I will distribute your homeworks to you next time, okay? And you will grade yourself. You have the model answer, you have the final, you have the model answer that I posted, right? So this is pretty much the thing that I will do if I have the homework. This is how I grade. You go with the model answer. If there is any mistake you did, any mistake, you have to take off 1 point. So every problem will be 10 points. So if an assignment with 5 problems, it will be out of 50. An assignment from 4 problems will be out of 40. So every problem is 10 points. And you go, you never give yourself 10 out of 10 unless you get the final answer correct, right? Otherwise it has no meaning. How to differentiate between yourself and somebody else who got the final answer correct. Every mistake you have to take something. And how much is this thing? The least. It's up to you. Half a mark, 1 mark, not more than 1 mark, okay? This is how I grade. So you have to take something whenever you see a mistake. Then you're going to return it to me. If I find that you didn't take something when you found a mistake, I'll give you 0 for the whole assignment, okay? I think it's a good deal. Okay, so I'll distribute to you your homeworks next time, and you will grade yourself, bring it back to me. Yes?
And if you make one mistake at the beginning and you keep that mistake along the way, does it mean minus
No,
1?
no. You take 1 for the first mistake, and you just assume that you got it correct. Continue. Okay? Any question? Okay, so this takes care of the homework, and of course I'll do the quizzes and midterm. Pretty much similar. Yeah. Okay, we're done. We're done with the course that is usually taught, and almost the second half will be extra stuff, but certainly will be in the final.
Question.
Yes, sure.
So can I forget everything I learned for the last 6 weeks?
No, Lagrangian mechanics is with us.
That was just a joke, sorry.
No. For the final or for today, yes.
Okay.
I'll mention it after a while. So remind me.
Today we are not doing Lagrangian. Today is not Lagrangian.
Say it again, please.
Today is not Lagrangian.
Yeah, but we just need to review everything. We're gonna like make a schematic, or what do you call it, taxonomy for what we have been studying so far. So here is Newtonian mechanics. And here is Lagrangian or analytical mechanics. Right? Analytical mechanics.
Professor?
Yes?
So are we going to do something European today or
Today?
today?
No. No. So Newtonian mechanics versus Lagrangian mechanics for particles. What's the Newtonian mechanics of a particle? What's that? P equals ma, right? So mr dot equal forces. This is pretty much it. Or, because it's not extra equation, or you can write the angular momentum version, which is the rate of change of angular momentum now, it's not the linear momentum anymore, is the moment. Equivalently, you can write about any other point, not necessarily a fixed point O, any other point. Now you need to take care of the motion of the point. So subtract the mass of the particle r from the particle to the mass cross the acceleration of the particle, the acceleration of the point. If it's 0, then it's a fixed point, or can be a fixed point, and you recover the first relation. For analytical mechanics, we start with the principle of virtual work, or in dynamics is the principle of virtual power. Principle of virtual power. It's simply nothing but this equation. Instead of F equals ma, F minus ma equal to 0, and we take the useful part of it. We don't apply it in all the directions, we just take the useful part of it. And how you take the useful part of it? So Fi minus Mi Ri double dot. This is the zero equation. To take the useful part of it, we dot it with the velocity coefficient, right? And we sum all over the bodies. This is indeed the principle of virtual power, right? Then we do Lagrange's equation. You can solve it using this one. Today, by the way, I will post the homework 3, which is due a week, on the Lagrange's equations, particles and rigid bodies. And one problem, you will solve it using Newtonian mechanics, using principle of virtual power, and then using Lagrange's equation. And after this problem, you will realize how Lagrangian mechanics will save your life now on. So using Lagrange's equation, you just get the kinetic energy, which is 1/2 mv squared, right? This is for the ith mass. So sum all these to put all the kinetic energies and potential, then you get your Lagrangian, which is T minus V. And finally, you have your Lagrange's equation, which is d by dt partial L partial Q J dot minus partial L partial Q J is your non-conservative load plus the constraint effect. So sum over the constraints, lambda K AKJ. Well, this non-conservative thing, it's just the work function. The force times the displacement or the virtual displacement or virtual velocity. So summation of the forces, non-circulatory of course, I dotted with partial R I dot partial Q J dot. This is what we did before. I equals 1 to n. This is the non-conservative force. So this is our Lagrange's equation that indeed saves your life. It's a very convenient way of writing down your dynamic equations of motion. If you have any question, please let me know. We're summarizing what we have been doing so far. If it's a rigid body, what do we have for a rigid body in Newtonian mechanics? I'll give you some time to write if you have. And the lectures are online, you can always go back and fill in the missing gaps. What is the Newtonian mechanics for a rigid body? Still F equals ma, but it's not any a, it's the mass of this, or it's the acceleration of the center of mass, right? This time it's not or, it's and. Simultaneously, you have to write down 6 equations of motion in general. 3 for translation and 3 for rotation. It's not or anymore. H, C, around the center of mass is the moment about the center of mass. Equivalently, if you're going to write about any point, it's very similar equation. Minus the mass of the body, R from P to the center of mass now, cross with RP double dot. Right? Almost the exact same equation, but now 2 main distinctions. This is the acceleration of the center of mass, and it's not only 3 sets of equations, it's 6 sets of equations, right? So we go here for the rigid body. We draw a line. Let's see the principle of virtual power, how we modify it. Again, it's the same thing. Force minus mass times acceleration, that is this Newton equation. I dotted with the useful part, so it's summation over the bodies or particles. Fi minus mass I times the acceleration of the center of mass of the ith body, dotted with the useful part. wait a minute. This was not the only equation for describing the dynamics of the body. You also needed the rotational version of it, right? So I have to add the second part. Again, make this equation as a zero equation, m minus hc dot, and take the useful part of it. So this is the moment at the center of mass minus hc dot, dotted with the useful part of it. What's the useful part? It's always the velocity coefficient. Partial omega, partial your velocity. Here was translational velocity, here it is angular velocity. Summation of all this is simply 0 for all j. Like here, it was also for all j. Right? Any question? What about the Lagrange equation? I mean, the principal visual power is a bit easier for sure than Newtonian mechanics. We admit that, and you will appreciate it more today after you see the problem and solve it. But we know that Lagrange equation is by far more convenient and easier. So how to do the Lagrange? Well, it's the exact same equation, no change. This red equation, the magic equation. But what about the terms? The Lagrangian is still kinetic minus potential. Now the kinetic energy for any I body is not only 1/2 mv squared. First of all, this v is v of the center of mass. But I have to add, this is very important, I have to add the 1/2 omega transpose I omega. And this is I about the center of mass. Okay? On the I body, that's one. So translational kinetic energy and rotational kinetic energy. Actually, if your body is at some fixed point, rotating about a fixed point, you can write down your kinetic energy as simply 1/2 omega transpose I O omega. So this is for rotational motion about a fixed point O. Your kinetic energy is simply just rotational kinetic energy. But now the I is not about the center of mass anymore, it's about O. We will maybe have a quick example on it now, right after this taxonomy. Still the magic equation, the red equation, now just added a little bit, one extra term in my kinetic energy, and I have the same procedure. T minus V, get your L, do everything the same. The constraint term is the same. The non-conservative load term is the same, but take into account that the applied loads for particles, it's only forces. For rigid bodies, can be forces and or moments, right? So I need to add to this term something for the moment. So the Q and the Cj here, Q and the Cj is summation 1 to n, the same thing up velocity coefficient. I have to add plus something for the moment. Any suggestion? What's that? Should be? Any suggestion? Exactly, the moment times velocity. It's power, right? So this is why we call it the principal visual power. The moment, the non-circulatory part of it, dotted with the velocity, angular velocity force. Okay? So these two boards takes care of almost all what we have been studying so far. I'll give you a quick example on about how to compute this 1/2 omega transpose I omega term. I mean, it's not that hard, but I'll give you a quick example. and then proceed with a totally new topic that actually you could have finished the course without this. So, any questions so far? Yes, please.
Can I ask a small question? So the I in rigid body is because of several rigid body together.
The little I index? Yes. Yes. Any question, please? Please, if you have a question, please. In the midterm is gone, right? We have 2 more homeworks, maybe 2 more quizzes or so. If you have any question, please do not feel shy. Any question? So let's have an example here. You remember this problem, we considered it before. We have a cylinder that is rotating with a constant angular velocity large omega. You remember this problem we did before. We have here inertial frame, say N1, N2, N3 vertically up. So this rotation may be represented by an angle, say, called phi. So N1 rotates to be E1, you should be expert on this stuff now. N2 rotates to be E2, and N3 is the same as E3, okay? Then this red vertical plane, what's its name of the red vertical plane? What's its axis? E1, E3. Please take it out, not to confuse yourself. In this E1, E3, this is the origin. We have some rigid body hanging down from this origin and is oscillating in a pendulum-like motion. Now we're going to make it a bit harder in order to do some training for ourselves. So the body will be a T-shape. This part is mass 2m and length 2l. This mass is m and l. And this angle is theta. Okay? So this this black body is oscillating in a pendulum-like motion. Actually, if there is no rotation here, it will be exactly a pendulum.